both the models. We also discuss at the end how your relational OLAP model is different than multidimensional OLAP model. OLAP stands for online analytical processing. So we first understand the basic key terms called dimension and facts. In order to understand dimension facts, we look at some real requirement. From all the requirement, we'll fetch the important information. So let me open some requirement, and from there we pull our data. So I would show you different way of presenting data, one for traditional way and one for your analytical solution, different way of organizing your data, and we look at first the requirement sheet. I'm going to open some of the financial reporting, little complicated, but this is a real world requirement from where we start pulling our metadata. So first concept we are going to start with, for a multi-dimensional database, what is dimension? So the first term is a dimension. So I have got one reporting requirement where it's a typical financial reports. From there we are going to pull out what is the dimension. The dimension is what, as the name indicated, if you go by the typical English term, dimension is called a view or a context towards your data, right? So this is my simple requirement where we are trying to capture the each year how many employees we have, how many employees head count, and how many new employees are hired, right? So when we plot a chart on top of this, it look like this way. Ignore this one. It look like this way. For each year, how many employees are available, existing employees and employees are hired. In this requirement, we are navigating the data. What is number? We call a facts. Facts are the numerics which are going to evaluate. Facts are certain measures. So we are going to calculate our total employees and new hires. In which context? What is my context? Is my year. So dimension or the context or the view towards your data is called year. In your traditional relational database, data is organized in a tabular format. This is the right way of looking at your traditional relational database like your Oracle SQL Server. Organized data, we call this transactional data because one row is called one transaction. The transactions span across multiple subject area. If you look at this row, it talks about in a country, there's one sales data is capturing. You can assume this information coming from Walmart. So every time the transaction happens, the system they use to capture the record is called the transactional system. So every time the transaction happens, they insert the record into this table. Now, what does this table consist of? One row is one transaction, and therefore we supposed to have a transaction ID. I would insert over here a new column called transaction ID. So transaction ID would be, for example, we make it T101. So one transaction happened in which country, which city, what is address. We have a geographical unit information, the product information, which product, which date, what was the store name, store type, what was sales amount, what was operating cost, and various other details. So in simple word, as a customer, when you walk down to the shop, buy something is called one transaction. So in your relational database, data is recorded in terms of transaction. But this is not exactly happen when you record the data in a multi-dimensional database. Multi-dimensional. So data is organized in terms of dimension. Dimension is called a view or the context. So same data we split into multiple subject area. So we split this in terms of subjects. I could identify subjects or a dimension. I have got one subject called a geographical unit. which is, in my example, is a country, city, province, or province, or an address. I've got another logical unit of data called products, product details. We have various information about products. This is my second subject area. My third subject area is called store. So I would split this model in terms of various subject area. Another one is store. And this way you continue to split this. So when I design in terms of relational database, this is how it look like. You see, I've got one table for one kind of information. So I've got one separate table which store all the products, one separate table which store all the customer, one table which maintain time, channel, promotion, and other details. So all subjects we split into one independent table, and this is called a dimension. Whereas in your transactional model, all information stored in one table, because it is transaction specific. This is subject specific. So as per this graphical view, your one dimension is one table. As per your requirement sheet, reporting requirement, dimension specifies the context through which you are navigating your data. So in this example, you are trying to evaluate expenditure from various contexts. So in this example, my dimension could be, we are trying to evaluate the revenue or expenses for various years. So what is to be evaluated? That's called fact. What? You are evaluating expenses. In which context? In the context of year, you have got year, and another context is your different line of business: customer care, finance, HR, and training. This is my, you can call them the line of business or business segment or business vertical. So you are evaluating your expenses in the context of time and line of business. You continue to look at another requirement in the revenue model. You're looking at the revenue from different segments of the business. So here your dimension would be banking, and you're looking your revenue for banking and financial sector, telecom, major market, manufacturing. So my dimension would be my line of business, right? Line of business are, we have got banking and financial sector, telecom. This is all your dimension. So what you're trying to evaluate in the context of all this, you're evaluating your revenue. So data is split into two pieces: dimension and the facts, right? And this is come from the core, from your requirement itself. So now let's see the formal definition of dimension first. So dimension is a qualifying characteristics that provide additional view or a prospect to a given fact. What does that mean? I show the same information in one more way. So same data is presented in multi-dimensional format. You've already seen how data is stored in a relational database. Now look at the data in a multi-dimensional format. So this is an example. You look at, I've got two dimensions. One is time, which is quarter 1, quarter 2, 3 and 4, and your various province or a city. And the intersection of time and city is your data, which is your sales. So this is the total sales. You call a total sales for New York and quarter 1, total sales. So that is what the definition says. Qualifying characteristic that provide an additional view to the given fact. And now this is two-dimensional data. Province and time is a three-dimensional data. Time, province, and sales manager. So one more view or dimension has been added over here, called another dimension is your sales representative. So you read this sales with the intersection of John, New York, and quarter one. Three-dimensional. So the more dimension you add, the more additional perspective add to the given fact. Same data, look at the different context. Now, the, the, the benefit of organizing your data in a multi-dimensional format, you can see the comparison and analysis become quite easy. You're the one, you can pay attention to these two cells, which is marked with the yellow color. You can see we can compare time over time sales growth, time quarter over quarter sales growth, how New York is performing from one quarter to another quarter. What is sales growth for New York from one quarter to another quarter, right? We can also, each intersection of cell, talk about one kind of analysis. So now we see over here, these two cells say yearly sales for New York, 1 year total sales for New York versus 1 year total sales for Texas. All possible combination, if you compare these cells, what information you can derive over here, how different provinces are performing in first quarter. Right. Similarly, it's a two-dimensional view. The more dimension we add, the higher or rich analysis we can obtain. So in this example, when you look at all these cells versus all the cells below, when you compare this, what does that business meaning of this? How John has performed, what is John's performance as a sales manager for entire year for all the province versus Mac. How John is performing in 2008. Right, it's a four-dimensional view, John, province, year, and your quarter and year, basically three dimensions. It's a one dimension only. It's cumulatively calling as a single dimension. So how John is performing with against your Mac. You can also compare this cell which says how John is performing for last 2 years. John performance for 2008 and 2007. Right? So all possible intersection, I would call all permutation combination of cell, brings certain businessful information to the business. Any meaningful information you can derive from here. It's only three-dimensional view. The more dimension we add, the higher degree of analysis we can achieve. Higher degree of analysis. So I got another dimension called store. And now when you look at this cell and this cell, what it says, the total sales done in online store by John in New York versus New York by John versus Mac. So we're comparing individual element for two salesperson in one kind of store. Similarly, if I compare all these cells versus all these cells, so what information I can derive? The sales information in online store versus direct store. Two kind of store, how they are performing in first quarter, where two salesperson. So the benefit of organizing data in a multi-dimensional format, it eases your overall analysis. And in a multi-dimensional format, data present in this way. And in terms of tables, the data is organized. Each dimension is stored in one table. So this is a subject specific. So as per the definition, sales, sales have a product, location, time dimension. Such dimensions stored in a separate table called dimension table, which contain only dimensions. So what does dimension table consist of? Dimension table, the dimension of the facts that are further described as a dimension table. Example of dimension tables given. Each dimension table has a primary key through which we recognize the dimension values. So you see in this model, each dimension has a primary key. I've got product ID is a primary key for product. Customer ID is the primary key for customer, time ID, store ID, promotion, and channel ID. So in addition to the other details, you have a primary key, which in turn join with your foreign key of your fact table. Now let's see what's a fact. facts are the numbers, right? When you aggregate them, it should bring certain meaningful information to you. So facts are numeric measurements. So everything you evaluate in terms of numbers, right? All the business elements are evaluated. You evaluate your revenue, expenses, plan, number of employees, target sales. Everything is a number through which you evaluate your business. So numbers are facts are numeric measurements that represent a specific business activity. And facts are stored in a separate table called fact table. In your traditional relational database, we don't distinguish between facts and the number and the dimension. Now, first look at your transactional model. In a transactional model, we don't have a facts and dimension separately stored. You see, facts or numbers are stored along with your dimension. They're stored separate. They don't have a separate model. We store them together. But when you design a multidimensional formatting, what do you do first? You take out all these facts and store in a separate table called fact table. This is the example. So all the facts which you see in Excel sheet stored in a separate table, I call them as a fact table, and in turn joined with dimension using primary key and foreign key model. All facts are accessed via dimension, because without dimension fact has no meaning. So the first point, fact has a foreign key. For product ID, there's a corresponding foreign key product ID over here, right? There's a product ID, customer ID, time ID. So there's a customer corresponding foreign key through which you are going to access the data. So let's first look at the formal definition and then we analyze. The facts are numeric measurement that represents a specific business activity. Facts are stored in a fact table. It's a centralized table, center of the star schema. We'll talk about what's a star schema next. Facts are used in business data analysis. Right? It could be something: cost, revenue, expenses, headcount, anything which represents a number. So all numbers are facts? That's not true. You can apply test whether a given number is a fact or not. A simple test. Are all number facts? No. How do you do this? So you apply fact test. How do you do this? You take two facts. I'll take a sales. One fact and take another fact called, for example, I have a employee ID. It is also number. So sales is a fact or not? Is it a fact? How do you find this? So you aggregate fact with respect to some dimension and check, does it have any meaning? So I would aggregate with respect to time dimension. So I aggregate, it's a January sales, aggregate with February sales, aggregate with March sales. Any meaningful data? Yes, it's a quarter one sales. So it's a fact. How? Quarter one sales are meaningful information to the business. So we can test, is it meaningful to the business? The answer is yes. Therefore, it's a fact. Let's take the employee ID. Employee ID is also number. I assume it's a 5-digit number. So I add employee ID. I add John employee ID plus Carrie and check. When you add two employee ID, of course it's not at all a meaningful information. Is it a meaningful information? Of course not. It doesn't add any value. When you add to employee ID, it doesn't add any value. Therefore, it's not a fact. So this way you can identify the given element is a fact or not. Sometimes there are instances, some measures are work as fact sometime and they work as a key. There are certain scenarios. We'll talk about them as well. So fact table, data is stored in facts in a fact table. So facts are mostly raw numeric items which you have seen. Fact table often narrow and few column at a time, but large number of rows. Why it has a large number of rows? In order to understand this, we can see. So I've got few facts. Actual facts are I've got advertisement cost, various kind of taxes, unit price, unit cost, amount, sales. A few facts, and I've got a dimension keys. A fact table is pretty huge. Why? You can look at this. So you read this. This is amount sales for certain product for certain customer at certain point in time. To even make it more easy, what I do, I form a fact table over here. Okay, let's form a fact table. We keep on adding one diamond at a time. So I've got fact table called fact sales. I've got a dimension called product, right? So I have two simple column, product ID and product name. So each product, every time the product is sold, the record is captured over here. So I would call this transaction ID. Okay, let's take a simple one. I also form a time dimension, which is very important. We have a time, all analysis require time. So I would have another dimension called time dimension. We start with time dimension. So I have a time dimension over here, in which year, in which quarter, which month, and the most granular data is day. And for first example, I even go to more granular details, and then I remove the granularity, year, quarter, month, time, and each minute. So you can see every time transaction happen, we record over here. In 2013, quarter 1, in the month of January, 5th of January, at 8:10, there's one transaction happen. So at this time, I have one transaction. So I would say at 8:10, I would have a key over here called day ID or month ID for given time the transaction happen. So I would say at 8:10, so this is my time ID, at which the time ID considered to be a most granular data. I would call this is a unique key. I assume at each minute, each second, the one transaction happen. With this assumption, I have a time ID which talk about each second one transaction happen. So the moment transaction happen at 8:10, about this transaction, which product is sold. So at this time, the product is prod ID 101 is sold. How much a sales of $100,000, $1,000, and sales, and what is the expenses associated with this. So how do you read this? You read at 8:10, product 101 sold with this sales amount, this with this expenses, right? At the same time, there's another product sold. Right? At same time, two products can be sold in two different stores. So I assume there are 100,000 transactions each day. There are 100,000 transactions, right? So how many rows you have? For each day there are 100,000 transactions, so I would have 100,000 rows over here at 8:10, 8:11, 8:12. I assume each minute the transaction happen, we record the information over here. So your fact table, if there are 100,000 transactions, there would be 100,000 rows in the fact table. So corresponding to each transaction, the information stored over here. So your dimension table are often static. They are relatively, they do not change very often. Product table would change only when I have a new product. Time dimension would change if I modify time hierarchy. But fact table change every second and every minute. Depends upon what is your refresh cycle. So the moment transaction happen, you record over here. I'm talking about real-time warehouse. Different kind of warehouse will come to them, those points as you proceed further. The point over here to pay attention. The fact table is often very huge and has got few rows. So we capture only two dimensions, time and product. You can also add more dimension. You may have a store dimension. So you have a store ID and store name. So the moment transaction happen, you also capture in which store. The transaction happen in which store. You add another column over here and say at this time this product store sold in my store ID S101. S101 store is New York downtown, right? And we sold product P101. P101 is your cola, right? So you say the total sales done on $1,000 at 8:10 for the product of 101, which is cola, at store S101 called New York downtime. So your fact table is often very, very huge, and you have one key for each. Corresponding to your primary key, you have a foreign key over here. So this is what even in my fact table has got how many record. I think it's shortened. Fact table has got often millions of records. Fact tables is always accessed via dimension. Now fact has no meaning. Now look at this without dimension. Now if you look only your fact, if you look at only your fact called 100,000 has no meaning. So look at your fact with the intersection of dimension. So when I look this fact only with my one dimension, when I look at this fact 1000, so I call this quarter one sales. It's a one dimensional view. So fact 1000 has no meaning unless you look at with some intersection. So now this is a meaningful call. 1000 is a quarter one sales. What is 1000? It's a quarter one sales. Now you further extend this. It's a quarter one New York sales. You see, I'm accessing fact with some intersection of dimension. It's a quarter one New York sales. Then you further add, it's a quarter one sales, New York sales done by John. So fact is always accessed with dimension. You do not access fact independently, which doesn't bring any meaningful information. So fact is often centralized table in a star schema model that contain facts which connects to your dimension. Fact has a foreign key and it contains the facts. You may also have a primary key which is a combination of all foreign key. A primary key of a fact table is usually a composite key which made up of all foreign keys. A fact table might also contain either the detailed fact which has been aggregated. So what does that mean? In a simple example, I could show you what does fact aggregation means. I have a fact over here called total tax, total expenses, right? Total expenses are further divided into one of the element called total tax. Total tax in turn have an element called, I've got sale tax and federal tax. So it could be hierarchical, when you say the total tax, total expenses, which consists of your total tax and salaries. Total tax is in turn divided into sale tax and federal tax. This is what it says. Fact table might contain either detailed level of facts. It's a detailed level of fact which aggregates. So when I say total tax, aggregation means naturally it's a sum of sale tax plus federal tax. Sale tax and federal tax, which in turn. At different levels. So this is one level, that is second level. Dimension we discussed. Now we discuss the organization of dimension and facts. In your relational database, often data is organized in terms of in ER model, right? This is called entity relationship model. The entities in the typical scenario are tables, and relationship is a joins, right? So I show you a typical ER model, and then we convert this model into to a dimension model. I show you one of the requirement sheet, sample requirement, where transactional model is converted to a multidimensional model. So this is also ER model, where you see your entities are, these are your entities, and this is your relationship. Entity could be table, or entity could be your dimension as well. So data is organized in terms of ER model. But data is organized in terms of tables, but there is no concept of dimension and facts. So we would convert this model into the meaningful dimension fact model. It's a core model which you have a typical environment. So data which is available in a transactional model cannot be used. We need to convert this into a meaningful format. So one of the way of organizing the model is called star schema. What is star schema? Star schema is basically one way of presenting your dimension and fact. And the objective of the star schema first is to fast retrieval of the data. So we have two different requirements. The objective of transactional model is to record day-to-day transaction. So when I say a term called record means generally in relational database context we call insert, update, and delete. When you say record, in the insert, update, and delete, and you often normalize your model. Normalize the model when you design a transactional model system. So my objective is to, the moment transaction happen, we insert this. So the system like your Walmart, your salary processing, sales order processing are designed to record day-to-day transaction. And typically your relational database was originally designed for transactional model. It was originally designed, right? And later on, so this is my requirement for transactional model. And the objective of multi-dimensional database, or we call OLAP, called online analytical processing. This is called OLTP. OLTP. Online. It means the moment transaction happen online, online transaction processing. The moment transaction happen, you process it and put into your system. Online analytical processing, it means the model designed for analysis. So two different model, two different objective. My objective over here to record the transaction, and here the objective is to design model for analysis. So when I say analysis, most often it's a select query or a read only. We need to select. So my objective over here to design a solution which give me fast retrieval of data, where my objective over here to design my solution to support, simplify my insert, update and delete operation. Two different side of the coin, two different requirements. So my star schema is primarily designed for fast retrieval of data. Right. First we look at the definition and look at the advantage of star schema. See, star schema is a relational database schema for representing your multi-dimensional format. Let me show you one star schema. This is your star schema. I club these two fact table. This is your star schema. Assume it's a one fact table. Okay. Now in this star schema, I've got one fact table surrounded by dimension. This is a format. This represented in terms of multi-dimensional format. Let me close this. Don't need it now. This is a multi-dimensional format representation. The same I represented in terms of tabular view, cross tabular view, and this is multi-dimensional format. So you see here, these are all facts. The numbers are facts, right? These are axes with the intersection of dimension. So my intersection is time, province, and sales manager. So same thing, you look at your fact called amount sales for which product, which customer, which at what time. So you always look at your fact with the intersection of dimension. So it's a centralized table. The advantage of fact star schema is designed to quickly process query. I'll tell you what does that mean. So star schema is relational database schema for representing your multi-dimensional format. It is the simplest form of your data warehousing that contain one dimension, one or more dimension, and a one fact table. Each dimension, there will be one dimension for each subject. Ideally, there should be one dimension for each subject. I have one dimension for product, one for time, one for channel. This is my star schema. One subject has a one dimension. It is called a star schema because the entity relationship model between dimension and fact resembles like a star. It looks like a star, therefore it is called a star schema. There is a one fact table in the centralized surrounded by a dimension. It looks like a star, therefore we call it a star schema. So I have one centralized very large fact table which has a point towards all the dimension. What is the advantage? I come to this. First I show you every time you process your data, how data is processed in a star schema. So if we relate with the business term, business query, this is how it look like. So maybe I like to check the total sales. Let's look at the query one. The total sales made in quarter one by sales manager John, right? when I need to write this query, the total sales done by sales manager John in quarter 1. So what fact I need in this example? Total sales. With respect to what dimension? I need quarter 1, which is my time dimension, dim time in this example, and what is other dimension? Other dimension is your a sales manager. Sales manager is my sales representative. Do I have any dimension like this? Let's check. So I would made a little change. The total sales done in quarter 1 in New York. So my dimension fact would be total sales for the dimension quarter 1, which is New York, quarter 1, which is time dimension, and New York is my region. So is my system address this question? You look at your requirement and look at your dimension intersection. It can be addressed. So we can evaluate. So that's a star schema. Now star schema, let's talk about the property of it. Star schema, in one simple word, we use when you want fast processing of the query. My objective is the objective of star schema, primary objective, reports quick access of the data. And the benefit of this is simple to understand. Let's go the properties one by one. First, you identify each process. Identify business process for analysis. So my business process over in this example, each dimension is one process and one logical unit. In my processing, I'm evaluating my product, which is stored in a separate dimension, customer in a separate dimension, time in a separate dimension. So each dimension is one business process. In fact, when you start analyzing your requirement, the first sheet, what you do, you plot your requirements in Excel sheet. This is called reporting wireframe. You put your requirement into Excel sheet, and when you analyze this, you start recognizing what dimension needed in each model. In each requirement, what all dimension needed. So you come up with a list of the dimension and list of facts, right? In all 5 dimensions, you need all 5 requirements. You need these dimension and these fact, and then you design the model. How do they relate to each other? What are the joinings? This is also a entity relationship model, but this is present in terms of dimension and facts. Then you look at put some sample data of each dimension to understand well the nature of data. For example, channel. What is sample data of channel? By looking at the sample data, we can easily identify the nature of data. For each dimension, I put some sample data over here. So overall, it is my process. So that is what the first says. You identify business process for analysis. So each dimension may be one process. It can be looked from other way around as well, from requirement point of view as well. You can look at your requirement and check, is my model address the requirement or not? Let's look at the requirement second. We would like to identify sales growth for last 4 quarters from different channel. We have got a different channels of sales. So what I need in this sales growth. So fact is a sales, which I'm trying to evaluate. In which context? My context over here is a time, which is quarter. Quarter is my context. And the second context is my channel. So does my model support this analysis? Does it support? Let's look at the query. Do I have sales? Yes, I have got sales information. This is available in fact sales. So I do have a required facts. Does my model has information about time? Yes. I have a time dimension called dim time. Dim time. Do I have information about channels? Yes, we have information about channel. Different kind of business channel. This is called dim channel. So you check, evaluate the feasibility of your model by looking at the sample requirement and try to address those requirements with your model. In the same, you will come up with a list of all the questions and evaluate your model against those questions and check, does my model meet all the requirement? If it does not meet, what is that? The meaning of that, you need to remodel. You need to add more dimension or add more facts, or you need to remodel your complete system. So that's the first point. Second point, you identify the measures or the fact. Yes, you in a star schema you have measures. You have a separate fact table which store the various facts. We have a separate fact table called sales fact which contain all the information pertaining to sales. Pertaining to sales. Then we have list of column that describe each dimension. That's called dimensions. We have a dimension, product dimension, which has information about various products, product channel description, customer dimension, which contain various information about customer. Each dimension has a primary key which uniquely identify the dimension. So product ID is the primary key over here, customer ID is the primary key, time has a time ID. You can look at the sample data as well to understand. Dim product, look at your sample data. Product IDs are unique, which says which product ID are the details about the products. Product description, product class, category, but product ID would be unique. It will not repeat. It doesn't repeat. Next says in a star schema, dimension table will not have in parent. I don't have a parent-child relationship in a star schema. What does parent-child relationship means? I have a, for example, for geographic region, I have a table called country. Under country, I've got table called city. Right, so the parent-child relationship. Or look at the another requirement. I have a parent-child relationship in another model. This is a right example of parent-child relationship. Right, region is a parent, store is a child, and you can identify by looking at the cardinality, one to many. In one region, there are many stores. Right, this is how you read. In one country, there are many stores. So this is a parent, this is a child. In my star schema, I don't have a parent and child relationship. In fact, we denormalize them and make a one table. You denormalize and make a one table. So you have a parent and child relationship. So we don't have such model in a star schema. You also have a term called hierarchy. Hierarchy for the dimension stored in a dimension table itself. What does hierarchy mean? For example, simplicity, you can take a time hierarchy. Is your year, you have in 1 year you have got various quarters. In quarters you have month you have days you have weeks, and then you have a day. Right, so this is your time dimension hierarchy. We do have a product hierarchy as well. So data store, this is my product hierarchy. Look at this. This is my product hierarchy. So I've got product line, product family, category, and name. So product line is a parent. Under this I've got product family, category, and name. This is my product hierarchy. Data stored in the product hierarchy, stored in your dimension. You can check this over here. The product line, family, category, and name. Data is stored in this format. So hierarchy also stored in a table. We'll talk about this Snowflake model later on, where your hierarchy can be stored in multiple tables. So what is advantage of star schema? So, we discuss advantage. As I proceed further, the one biggest advantage you have is a performance increase. The data access from a star schema is faster. We'll compare star schema with Snowflake model, and I prove you how star schema is faster than Snowflake model. Star schema also has a two term called slicing down and easy understanding of data. It's easy to understand. We can slice down. Slicing and dicing is easy. Drill down and drill up. What slice and dice means? I think I don't have a model here. Slicing, tomorrow we discuss Snowflake model. We also discuss comparison between, we compare Snowflake and star schema, and we see which model should be used in which business scenario. And then I'll talk about various operations in multidimensional database. We also discuss about the overall view. Where does your multidimensional database fit into enterprise warehouse? So in enterprise data warehousing, we'll discuss about the place of multidimensional database. Where does multidimensional database fit into picture in enterprise warehouse? This is what we are going to discuss in tomorrow's session. And finally, we'll all talk about a type of hierarchy and various kind of operation. So I'm stopping here now. We continue our discussion in tomorrow's session, and this is open for your question. If you have any question, you can ask me.